Hello again. Um, in my blog, I did a post about unpacking a Teambot sample, and I stopped after the unpacking was done. So here in this video, I am going to continue where I left off, and in between making this video and the blog post, I got contacted by a member of the community, which I am very, very thankful for. I'm always really happy when people come in, read my blog posts. I'm really grateful for that. So I don't want to name this person here, but thank you for reaching out. It means a lot to me. So um, the person in question sent me a link to this website, cybergeeks.tech, and this is an article called "A Detailed Analysis of the Stop DJVU Ransomware." This was posted on October 31st, 2021. So it's been a while back. And you can see here that it says, it talks a little about this Stop DJVU ransomware. And it says that this ransomware can run with one of the following parameters: admin, tasks, autostart, for netres, and service. Let's look into this. So here in the technical analysis, an analysis is done, and when we just come down here, it talks a little bit about the unpacking process. Now, the interesting thing is actually, if we come down to this part, it says that the internet read file operation is used to read a response from the server, and up here it says the malware performs a GET request to API 2IP.ua du.json. Now here on the left side is the unpacked Teambot sample in Github, which I further analyzed. And if I go to this MW check location function, of course it wasn't named that, I labeled it that, you can see that it does exactly that. So it reaches out to this geo 2IP JSON, and it gets the country code, and then it checks the country code against a couple of countries, and it's exactly the same as here in the blog post. A couple of changes are here, maybe a couple of countries are added here because I can't see this. Oh no, it seems exactly the same. So it checks the country codes, and then it does an enumeration of them and says, okay, if we're running in any of these countries, then we're just going to stop execution. That is what this routine does. So next, we can see that there is the set priority class high, which I have here. So it's also exactly the same. And then it says the malware runs with minus admin, task, auto start, etc. And we can see that down here. So it says is auto start, is task. This differs a little bit. And what then happens is that it creates this personal. Just let me see here. Skip this part. Personal, if I could type. It creates this personal id.txt, which is also the same in my analysis. But the part where it differs is here in the malware, in the part that I analyzed. It performs a decryption of the URLs, of some URLs, and it does this with XOR 80, as it is also shown in here. So there is, I think, if we search in the article, we have this decryption happening here. And you can see that in this case, it decrypts securebiz.org. In my case, it decrypted different URLs. And then from these decrypted URLs, it performs a download. So if we look at the article from the beginning again, we can see a couple of additional things, and this pretty much lines up perfectly with the stop ransomware. Now, if I take the initial sample, which was labeled as Teambot, and throw it into any run, we can see that here it actually even tells us it's ransomware stop. Now, the problem which I have here is that even though the executable that I have lines up perfectly with the analysis here in this article, which was sent to me, I wasn't able to get this to encrypt anything. So to demonstrate this, I am going to show you on my Windows machine what happens when I actually run this. Okay, so here on my Flare VM, I have the sample in question, and what I'm going to do is I'm going to start procmon, and I am going to just a sec. Let me set this up a little here. I'm just gonna do rename, copy the hash, and then put it here into the filter. So I'm going to take out these filters which are present right now, go to process name, I'm going to say contains, and then put in the hash. Add that and start running procmon. Now, it says in the article that when you run this ransomware and it can't reach out to the internet, it will use a hard-coded public key and then do the encryption. So that's what we're going to try out now. So I'm just going to disconnect my network. I've done that, so you can see I don't have any internet connection, no fake internet connection whatsoever. And if I run this now, this should actually encrypt the system. So let's execute this and just wait a second. So there's actually nothing happening here. This is clearly not encrypting, but the article is from 2001. So the malware authors, of course, they might have made changes to this in a sense that that it actually needs to reach out to the internet. Maybe it doesn't use this hard-coded key. Maybe something in my configuration is in my analysis environment is wrong, but I can't seem to see any encryption here. All right, so even if I wasn't able to get this to encrypt anything, I think that when reading through this article here, it becomes clear that this is actually stop ransomware because it, or at least the stop ransomware loader, incorporating the stop ransomware, because this just lines up perfectly with the article, almost perfectly. But of course, this article is from 2021. This is an older article, a new sample. So of course, there will be some changes in there. Adding to this is, of course, any run, which says when I load up the sample, it's ransomware stop. And also, if I load the sample on VirusTotal, I get a lot of these. I get stop ransomware here, rackcrypt. We have something down here, maybe Trojan crypt. So again, ransomware stop down here. So that pretty much tells me that this is not Teambot. This is actually stop ransomware. So at this point, I want to give a big thank you to the person that contacted me, reached out to me, and told me about this. Um, I'm always really happy when people hit me up. I'm always really happy when people read my write-ups, when they come to my YouTube channel, when they come to hang out. So I'm really grateful for that, and again, a really big thank you. So at this point, what I want to do is in the next video, I want to let this run, and I was able to get my hands on the executable, one of the executables that this downloads. So we're going to have a look at that. Hello again. The website you can see here is my blog. It's 0xca7, so cat at github.io. And the last little write-up I did was called Teambot Unpacking. So here you can see the sample hash and read through it, and you will eventually, when you read through this, be able to unpack the malware, and this just shows a couple of the internals. Now, what I want to go into today is a little bit of the dynamic analysis of this malware. Now, for this, we're actually going to take a little shortcut, and that is I'm just following this link here to Malware Bazaar, and come down here, and you can see that there is some threat intelligence available, and also something from any run here. So here I'm going to visit this link, because the thing is, if I run this malware, it tries to download from a specific URL, but this URL is defunct at the moment, so it's not available anymore. For that reason, I am going to use the analysis from any run to actually figure out what this is downloading. So I've identified the two URLs. The one is this seret.top, and the other is this fuyt.org. Now, as you can see here, this is just HTML, which I don't really care about. But here a download is actually made of build2.exe. So let's get this. I've just clicked on it and hit download. So let's get this. I already downloaded this once because I've analyzed it before doing this video. And what we can also see here is that there are a couple of downloads of libraries. For instance, this Moss Glue or NSS3DLL, and we'll get back to those later. But for now, what we're going to do is we're going to analyze this build2.exe. Before we go into the analysis of the dropped executable, I want to do sort of like a little sanity check. So here you can see the original Teambot sample that I had for my unpacking blog, and I am just going to run this and use procmon to just record what this is doing. Then we're going to look at the result in proc.dot, and also I have a internet simulation and Wireshark running on my virtual machine, my Linux virtual machine that is. And then we can also look at the traffic so that we can see that we get the same results as we saw in any run. So let's set up procmon real quick. What I am going to do here is just stop this, and I'm going to make myself things easier for myself. I'm going to rename this to tb.exe, and then here in procmon I am going to say process name, and then I always do contains and just say tb.exe. So I'm going to say OK here. I'm going to add the item, and now it's capturing only what tb.exe is doing and not anything from the other processes. So let's run this. Already a lot of things happening, of course. Let's just let this go for a while. You can see clearly it downloads two executables. One is this build3.exe, which we didn't see in any run, but what we did see is this build2.exe. And also from the internet simulation, you can see that these programs are not just downloaded, they're also executed. If they were just downloaded, we wouldn't be able to actually see this here. In case you've never worked with inetsim, when you have a piece of code that wants to download an executable from the internet, inetsim will supply it with a default executable, and that is this executable you can see right here. So let's stop the capture and save this. I'm going to save it as a CSV, and I'm going to save it on the desktop so we can have a look at this in Procdot. We can close this up, open up Procdot. This just takes a moment. And then we will go ahead and just open this log file. Here I'm going to select dump and then do a refresh. And this will generate a graph for us so we can see what's going on. And already there's lots of stuff. That's why Procdot is such a nice tool, because it's easier to read this than to read the whole output of Procmon. So first of all, let's zoom in here. You can see that there's a lot of TCP traffic happening. This is my Linux machine, or the IP of my Linux machine, that is. And we have all of this TCP traffic. What's also interesting up here is that the malware seems to create a file, and that is under C, system ID, personal ID.txt. So let's have a look at that real quick. Go to C, and then we'll go to system ID and then personal ID.txt. Just open that up. I don't know why this is taking so long. Maybe I didn't click correctly. Now there it is. So this looks like pretty much maybe a fingerprint of the system. And if we come down here, we can see that these files here are downloaded. There's also something created here, just a TXT file. So that is pretty much that, what we can see here. I don't know, there doesn't seem to be anything more interesting. This is just DNS resolving, I think. And up here, this is also not really interesting. So I'd say we now go over to the Linux machine and have a look at Wireshark. Okay, now we have Wireshark open, and the first thing that I maybe want to filter for is we could do DNS, and then you can see these two domains that we saw in AnyRun, the serit.top and this fuyt.org. These are both contacted here as well, or at least there's being an attempt made to contact these. And if we look at the serit.top, we can see some HTTP traffic, and eventually there's this getDL build2.exe. Now here for fuyt.org, there doesn't seem to be anything going on. As we saw in AnyRun, there's no executable being downloaded. So now the question becomes, what is this build2.exe? And that is what we're going to find out now. Alright, so I put this on my Windows machine, this build2.bin, and let's go and, I have detected easy here. So we'll just put this into detected easy, and then we will see how it looks. What I'm interested in here is more or less I want to see the entropy, and you can see the entropy is huge. So this is going to be packed, and it's going to be the text section. Then let's maybe look at the strings, if we can see anything interesting here. Just a quick look. We have kernel 32 DLL, which is expected, and these languages, this is all normal, I would say. Then here we can see some weird strings. We have a local alloc. Here we have some function calls, virtual alloc, get proc access, proc address, sorry. This is all pretty much expected. These copyright strings, these might be interesting. These might be some sort of an indicator. I also saw one here. So this copyright string here. For further analysis, I'm just gonna pull out the strings and save them in a file on my Linux machine. But for now, I'd say we get on with finding out what this actually is. What we can do here is we can rename this, and then we'll make a exe out of it so we can execute it. And we can see we get the same symbol here. Now from any run, we were able to see that there were some DLLs downloaded, and these DLLs, if I remember correctly, they may be associated with a stealer that I have looked at in the past. So no spoilers here. Let's put this into x32dbg, and then we'll start debugging. Okay, now the question is, where do I want to set my breakpoints? Well, I will do a breakpoint at virtual alloc. I want one at virtual alloc x. I want one at write process memory, and I want one at resume thread. So what I'm looking for here is pretty much, because this is packed, I want to get to the unpacked part. So that's why I'm doing virtual alloc. I'm doing write process memory in case there is some process injection going on, which in my opinion would be or could be very likely. So we will just go ahead and run this. We're at the entry point now, and then we will just let it go. So this takes a while. We get the first virtual alloc. Oh, forgot one. I want one at virtual protect as well. Okay, so we're gonna return from this call, and we have the address of the allocated memory region in the EAX. So let's do a right click here and say follow and dump. And then I'm gonna actually set a hardware breakpoint, and I'm gonna say break here at access. So let's run. We have 1 byte written, and then this is populated with quite a lot of stuff. There's some readable things here, which is pretty cool. This doesn't look like a MC file, so an executable. There's also all of these CCs in here, which are traps. And we've hit the second virtual alloc. So let's execute until return, take the return address, follow and dump, and we're going to follow and dump too. So here we are, going to set another breakpoint hardware. So that went a little fast. Breakpoint, and then a hardware breakpoint, and then at access. Run again. Then we have the name of the executable here. We're just gonna run or keep on running this. This is hit again. So we're gonna run again. We have another virtual alloc. So execute until return. We do not have to follow this because it's the same memory area that was alloc before. So we're gonna keep on running. We see that there's 1 byte written here, or 4 bytes actually. Let's run again. And this here, this part down here is now written, and we hit virtual alloc x. So I am just gonna keep on running here, and now we hit write process memory. And this is pretty cool because something is being written to another process's memory with this. And down here in the call stack, you can see that there is this MZ, and that is an executable. So we're going to do a right click here, and then we're going to say follow and dump. And what we get now, if we scroll up, is we can see here PE, and there's the MZ. So I'm going to do a right click in here, anywhere at all, and then I am going to say follow in memory map, and then we see that this memory region here is actually marked as execute read write. So that is interesting, and I am going to dump this memory to a file. We're going to go to the desktop and save that. I'm going to leave the debugger running for now, and then we're going to take a look at this in a hex editor. So we have HXD. I like this one, so I'm going to use it. Of course, this would work with a text editor on Linux as well. And we're going to open up this file. And here I can do Control F to search for MZ. And you can see we're here. This is where our program starts. And all of this stuff up here, I actually don't care about. So I'm just going to highlight all of this, and then I'm going to delete it. But before we do that, you can see here, this is the first virtual alloc here, if you remember this byte sequence. But we're just going to delete it, and then we have our file here, and I just saved that with Control S. Now we have a backup file that is generated by HXD, so that is the unedited version that we just opened, and this here contains the edited version. So now let's take this and rename it to build 2, and then I'm just gonna call this unpacked so I can remember it more easily. Okay, so let's load it into die, and now let's look at the imports maybe. So the imports look good. We have a couple of new things here. The most important part, or the most interesting part, are the strings now, because this is what gives us a first indication of what this might be. So these strings here, like this one, they look like there's something encoded here. And if we go through this further, we can maybe see something else that is interesting to us. So let's scroll through this real quick. There seems to be more of these. And I just saw something that was interesting. So here we have something with a wallet. Now I'm not I have no clue about crypto, but I've seen these in quite a lot of stealers, like these wallet names, which is interesting. We also have an IP. We saw this IP in AnyRun, I think, and we also have this Outlook profile stuff. Files outlook.txt. Okay, so this looks like, from a first glance at the strings, this actually looks like a stealer. We have more stuff here, which might be interesting. We have Mozilla. Okay, we have profiles ini. Select URL from URL. So this is a SQL query. That is interesting. We also have Telegram desktop key data, and so on and so forth. So this looks a little bit stealerish here, and the entropy now looks halfway decent. I think we unpacked it, at least a large part of it. So I'd say let's take this and put it over on my Linux machine, and then we will continue with the analysis. All right, so I'm back on my Linux machine, and I put the unpacked executable here in a folder called dropped, and I'm just uploading it to VirusTotal and see what VirusTotal tells us. So this tells us we have VDAR, VDAR. This is SUSE. I don't know how to pronounce that, but it's uh, I think from this here, from these detections, we can safely say that this is malicious. Um, we can also have a look at it in any run potentially, but for me, I'm just gonna load this into Ghidra, and let's let the analysis run through. So as I was saying, I had a look at VDAR in the past. I unpacked it and looked at the internals, but I didn't actually put anything online about it. So if this actually is VDAR, then we can maybe I can maybe use that past knowledge to my advantage here when analyzing this. And the second thing that I want to actually show you is if we go out to Google and we do this mouse glue DLL and see what it does. Okay, this is all German. This is English. I think it was something. I think it was something to related to this DLL allows you to get some profile information or something. If it really is this mouse glue DLL that is being downloaded, as we saw in any run, it definitely isn't malicious. And we also saw this NSS3, which was downloaded, and I don't know exactly what that is, but I also found out, if I look through these websites, this is actually also not malicious. Here it says, is a part of the network security services and developed by Mozilla Foundation. So these seem legit. I'm not going to go through these other websites. So I think it's just the stealer getting components that it needs to actually read out information from the browsers or from other programs. Okay, let's go into the exports and then go to the entry. I'm going to use the decompiler because in these videos it's easier to work with that. Now, here you see this win command line, and this local 24 is being returned. So this is going to be the main function most likely. So I'm just going to call this main, and we can jump into that. And this is exactly what I saw in the first analysis of VDAR that I did. All of these sleeps, and then you have this structure with a couple of functions in here. The main part that is interesting is actually this function, because you can see here there is like this while true where there are just these sleeps, and this is the last function call before that. So if we open this, you might notice that it takes forever to decompile this because it's a huge function. And this is where the main stealer activity is going on. So let's look at the function graph. You can see that this is just huge. And in here we have a lot of interesting calls. So if, for instance, let's just go and search for the strings maybe, just so we have those open. You can see that this mouse glue is being searched for. We saw this in any run. We saw this. So these functions here are probably going to just load up these DLLs at some point. And let's go back to the main stealer function. And I'm going to rename this. So I'm going to say MW stealer main, because this contains the main functionality. When I did my initial analysis of VDAR, of course, what you're going to have with the stealer is it's going to collect all of the data, right? So it's going to collect all of the data, and then eventually, if you come if you actually come down here, at some point it's going to exfiltrate that data. So that is actually where I want to get to. So what I'm going to do here is I'm going to go through this step by step. If I remember correctly, I think this function decrypts these weird strings that we saw. It also takes forever to decompile because it's a huge function. So let's just wait for that. What I also recognize is this error. Yeah, here you can see that. This is just a heap of these functions being decoded or decrypted or whatever you want to call it. Okay, so we're back. We're here in the string decryption function. I renamed it to MW decrypt strings. I have here as the first parameter, I have the decrypted string. Then we have the encrypted string as the second parameter and the length as the first parameter. Because if we go to the caller of this, just jump over there, it takes forever to load. We saw that this was a huge function, so the decompiler just takes a while. We can see what is actually that these parameters are actually correct. So let's look at line 9 here, at this line. You can see that we have this this part here. If we double click on that in the listing, you can see it's some characters here. We have this part here. I just called it encrypted. This is actually the SOR key. And then we have the 6, which is the length. So let's just correct that. Let's just call this SOR key, and then we're going to call that the encrypted string. Okay. Now, this tripped me up a little. To be honest, there's a couple of things here that look weird. So I decided to go into the debugger and have a look there. Because as you can see that here we have this local alloc, which allocates the memory. This is being returned. In here we have this SOR key. And what tripped me up a little bit actually is this PBVAR1. As you can see, it iterates through this allocated memory because it's always the pointer to the allocated memory plus I. So it's going to iterate through this, and this is where the result of the XOR is going to be stored. And then there is this part back here which just says enc minus pmem. So it takes this encrypted string, and from that it subtracts this pmem, so this address. That tripped me up a little. So we're gonna look at this in the debugger just to show that what actually comes out of here is that simple. Alright, so I've loaded up the malware in X32 debug, and I've set a couple of breakpoints. So we're gonna let this malware run. We're at the entry point now. We're gonna run again. Now we have a first chance exception. We don't care about that, so we're just gonna keep on running. And it takes a little while for us to reach this, what I called steal and main. We're gonna run again, and now we're inside of the string decrypt function. Here I set a breakpoint at this local alloc already. I'm gonna set a breakpoint here at the end of this nested loop, which does the string length calculation. I am going to set a breakpoint. I'm gonna remove this one. I'm gonna set a breakpoint at the XOR, and you can see that the result of XOR is going to be stored in AL, and AL is going to move to this memory in ECX. So we're also going to set a breakpoint here. Let's run this once and step over the local alloc to get the address of the allocated memory, and I'm going to put that in dump3. So this is our allocated memory. Now we can hit continue to come down here. We saw that this should calculate the string length. We said that ECX is going to contain a pointer to the first byte of the string plus 1, so to the second byte of the string, which we can see here. This is exactly what we expected, and it's going to be subtracted from whatever is in EAX, and that is going to be the pointer to the end of the string. So let's go here, and indeed it's the end of the string. So let's run this. No surprise, we get this f here, which we already got passed in as a parameter, and it's going to be stored in EBX. So already here you can see we pretty much don't need to calculate this really, because we already know the length of the string. So this already seems kind of useless. Now comes the interesting part, because we saw in Github that there was some jumping around in memory, which I couldn't make sense of in the first pass. So let's come down here and we can see the XOR operation happening. So we're XORing the value in AL, which is this 50, so the lower byte, so it's 50 up here, and whatever is in EDX plus ECX. So let's follow this in the dump and see what we get here. So we're going to follow that, and we have 19 here. Okay, so we're XORing 19 with 50. Let's see what should come out of here. So let's do 50, and then XOR, and then we're going to do 19, and this should be 49. Okay, let's let this run. We have 49 here, and this 49 moves to ECX. If you remember, here in ECX you can see this address, and this is exactly the address of the allocated memory, which we put into dump 3. So this is going to move here, and we get an I. Now let's remove the breakpoint at the string length calculation, because that is really boring, and also we can put a, I already put a breakpoint here at redx. I just put a breakpoint at the return, so in case that I overextend and by accident jump out of this loop, I have like this safety breakpoint here. So let's run. We come here, and we can see we have again XOR, and it's this time 51, and then we're gonna follow this EDX plus ECX in the dump. So we're gonna do that. And notice this ESI here is actually being incremented. That is the index to the pointer in memory. So we're at index 1 now. Okay, so I followed this, and this time it's 1F. So what we are XORing is actually 51 and 1F. So let's do that. Let's do 51 and XOR that with 1F. And the result is this time 4E. So let's look at the dump 3. We're going to do the XOR. As expected, it's 4E as a result. And we're going to step over this, and then we have in. All right, so now we have a pretty good understanding of what's happening here. And let's just run this till the end. And you can see the result is insert key here. Now I want to show you something interesting in CyberChef. So let's go over to the Linux machine, and then we are gonna get behind what is happening here. Okay, so here, string decryption function. Again, we saw this in action. We had the 1F, we had this value, and we had whatever this points to. So this encrypted string is here. I copied out those bytes and just threw them into this text editor here, and also the SOAR key. And if you throw this into CyberChef and you say, okay, we have from hex and we want to XOR and put in this key, we get exactly insert key here. So what is actually happening, regardless of this jumping around in memory, which looks pretty complicated, is we have nothing more than XORing string 1 with string 2. So the function that we see here with this jumping around in memory actually comes down to just taking string 1, taking string 2, which this was the SOR key, this was the string in memory, and XORing the bytes together one by one, and then we get the result. So this simple C function is actually what is happening here. The result is returned, so it's allocated on the heap, and as you can see, pmem is returned, and then we can see that it's stored in here. So that's pretty much it. Okay, so now that we know this, we can actually build a script in Github. So what I did was I went ahead and built two scripts, vidar single and vidar deobfuscator. What I pretty much have here with the single is if I run this, I coded it in Python because I'm actually not a Java expert. We have address 1, so we can take this and just enter it. We can say 0x 48 C2B0. And then it says it wants address 1. The problem is I can't reach that address in memory at the moment, so I'm just gonna have to actually go here. Yeah, this script is not optimal, but it does kind of serve its purpose. Go here, take this from the listing view. So it's pretty much 0x, this one and this one. And notice that these are directly underneath each other in memory. So you have the SOR key, and then you have the encrypted string. And again, here you have the SOR key and you have the encrypted string. So that's going to come into play later. But first of all, let's run this this decryption script. So we're going to do single again. And here we're going to enter the first address. Yeah, we got that. We're going to take the second address, put that in, and we enter the size, which was 15. We're going to say OK, and then this is going to run through. And then in the decompiled view, we should actually now see what comes out of that. And I think it's here in the console, scripting in the console, it says insert key here. So now this is a first step towards automating this decryption of the strings. Okay, what we can do now is we could go through and do this all per hand, but that's not very good and really slow. So I wrote this vidar deobfuscator. If we run this, it is just going to run through, I hope. I think it takes forever to actually do its work. Okay, so the problem here is why doesn't this work? Well, because I initially in the Python script I put decrypt string. So I'm going to rename these, and I'm just going to say decrypt string, because the Python is trying to find references to this decrypt string function, and then it's going to run through. So this is just going to take a while to decompile, and then we can run the script again, and hopefully get this going. So let's do a double click here again so it can run through. And this is going to take forever. And you can see the decompiler running again. And what this does is pretty much going to do the decryption for us. And then it's going to put the comments up here, which tells us what all of these decrypted strings are. All right, look at that. It finished decrypting. Now that the problem here is with this with the script that I wrote, it's like the worst Github script that exists probably in the history of all scripts of Github, and it doesn't always work, but it shows you a lot of things in here which are already pretty telling. For instance, we have this this part up here, this user agent identifier. We have API faceit.com. We have, for instance, if we come in here, passwords.txt, login data, files autofill, cookies. So this all looks like a little bit like a stealer already. We have these MOS logins, encrypted password, a lot of SQL queries. If we come down here, there is Thunderbird profiles, so it's already a little bit telling. Telegram also, and so on and so forth. All of the browsers, and a couple of these strings weren't decrypted. I probably still have to do some work on the script to get this a little bit more refined, but it's a start. All right, now, so to wrap up this video, I am back here at the any run of the Teambot sample, which actually turned out to be the Stop Ransomware, which I got from Malware Bazaar. We can see here we have a ransomware stop, and then we have VDAR. And when I took this build 2 exe, which was downloaded, which was VDAR, and ran it, you can see down here it tries to download these DLLs from this IP here, and it also tries to contact this website here over HTTP. Now, when I run this, it pretty much does nothing. It doesn't start the stealer function just because it can't reach out. So having identified this now and having this quick look inside of it, I think because this video is already running for about 40 minutes, I'm going to call it a day here. What does that leave us with? Well, we had the sample labeled as Teambot in the beginning, which thanks to a member of the malware analysis community was then identified as the Stop Ransomware. We also saw that this malware downloads an additional executable, which we unpacked and identified as the VDAR stealer. So in a future video, I might dig a little bit deeper into the stealer, maybe get a more current sample of it. And with that being said, thank you very much for watching if you came this far, and I hope to see you next time. Goodbye.